Hi, I'm Penny, from a PhD student from Singapore University of Technology and Design. So today I'll be sharing with all of you our work here on mouse authentication without the temporal aspect. What does a 2D CNN learn? So user biometrics authentication for computer system, they can be divided into two different categories. The first category is the physiological biometrics, which is also the predominant approach in this field. So an example of such biometrics is iris scanner. So it is accurate and reliable. However, it is costly as we often require additional hardware to be deployed. So as an alternative, one can opt to use a behavioral biometric such as keystrokes or mouse dynamics. And these biometrics, they can be easily integrated into existing systems and are also cost effective. So motivated by the success of deep models in other fields, here we investigate the usability of deep neural networks in a mouse-based authentication system. So given the time series mouse data, it is natural for us to employ a time series-based model such as LSTM or 1D CNN. But however, here in this work, we choose to use a 2D CNN model. And if you think of it, it may seem strange because the 2D CNN model actually removed the temporal information from the data. But however, here our choice is mainly motivated by the fact that most publicly available mouse datasets, they are relatively small in size, which makes learning deep models from random initializations of weight difficult. But with 2D CNN, we can use transfer learning to initialize the kernels in the convolutional layers with pre-trained weights. So here are the key contributions of our work. We propose to use a 2D CNN model with joint multi-label training and have compared it with a classical SVM method and a 1D CNN baseline. We have also explored different pre-processing methods to convert the raw mouse sequences into suitable inputs to be used by the 2D CNN. But however, due to time constraint in today's presentation, I will not discuss the experimental results for the different pre-processing methods. So for more information, you can refer to the paper. Our third contribution here, we did also explore the robustness of our proposed 2D CNN method against changes in the environment. And finally, we visualize what parts of the mouse curve are actually used or has contributed to the final decision of the network. So we have two baselines here. Our first baseline is a classical SVM model which uses a fixed feature extraction of 66 features. So these 66 features are based on a 2012 paper. So some of these features are speed, acceleration, or angle. And we have another baseline, which is a 1D CNN model, which receives an input sequence length of 130. So each element here in the input sequence length is a time normalized vector. So figure 1 here, I'm not sure whether can you see or is it too small, is our architecture of the 1D CNN baseline. So as mentioned, we choose to use a 2D CNN here. So we have chosen the GoogleNet architecture from Cafe package. And we observed that fine-tuning all layers for this network works better than fine-tuning only the last layer. And since at test time, what we are interested is, given a sample, we want to know whether this particular sample belongs to a user or not. So to use a multi-class classifier here would be inappropriate. Instead, we should consider n different binary classification problem, in which n is the total number of users. So we discovered that training the network jointly over these n binary classification problems, it improves performance as it reduces overfitting by learning a common set of features, and also it reduces the total training time taken to train n different binary classifiers for n users. Because instead of training n times, we only need to train the classifier once with n different train the classifier once with n different binary outputs. So figure 2 here shows how we have adapted the GoogleNet model to support this type of training. So our study here uses two different datasets, the Balabit dataset, which consists of a train and a test set, and the results for Balabit were reported on the test set after removing illegal sessions. And we have also performed the same experiments on TWOS. And in TWOS, there are 24 users, but here we have randomly omitted 4 users here to be used in a future test case to test our trained classifiers with samples from unseen users. And since TWOS doesn't provide us explicitly with a test set, so for fair comparisons, we have reported the TWOS data on the average of a 5-row cross-validation set. So table 1 here shows the comparisons of the proposed 2D CNN method with the SVM method and 1D CNN method. Note that the LSTM model here computed is a new experiment that is not included in the paper. We thought it would be interesting to see how a popular candidate for time series-based models such as LSTM would work on such mouse movement data. Also note that the fixed features SVM here appears to be a tough baseline, and the 1D CNN model and the LSTM model appears to perform differently on both data sets. But one thing that is consistent here is that the proposed 2D CNN method consistently outperforms the rest of the methods on both data sets. So the results reported in table 1, we have considered one single curve to be one samples. But if we refer to our paper, we also have these experiments in which we average out the prediction scores of consecutive samples, and we see that when we increase the number of curve, when we average out the consecutive curvelets, the predictions become more reliable. So seeing how the proposed 2D CNN method outperforms the rest of the models, we are also interested to see how robust is this 2D CNN model against changes in the environment. As such, we have performed the following two things. We have removed the position dependency by translating the minimum bounding box of the curve towards the center of the plot. And on the other hand, we have removed the resolution dependency by ensuring that the screen resolution during test and train time that they are different. So we simulate such a change in resolution by simply shrinking the mouse curve towards the top left corner as a form of a simulation to simulate an increase in the screen resolution. So looking at table 2, once we remove the position dependency as shown in row 3, it seems that the AUC and ER is only affected slightly. However, once we remove the resolution information, that is, we ensure that the screen resolution for tests, they are different from train, we see that the model's performance is affected badly. So this issue here needs to be tackled for serious usability of the model in actual application. But frankly speaking, there are also other things that we did not consider in this paper. For example, we did not see whether is our model dependent on a specific task or whether a change in this task affects the user's behavior and what is the overall impact of this change to the model's performance. We consider this as interesting questions, and we would look at it maybe in our future work. And another thing that we are curious about is what are the features that are actually learned by the 2D CNN, since I've mentioned earlier that the 2D CNN actually removed the temporal aspect from the data. Precisely what are the positive evidences that supports a prediction and what are the negative evidences that goes against a prediction? So for that, to answer that question, we have employed the layer-wise relevance propagation method, which decomposes the classifier's prediction into a relevance score for every pixel. So it is based on this conservation principle in which we ensure that the sum of the relevance scores over all neurons at each layer they are conserved. So applying this conservation principle from the last layer, which is the final prediction score, all the way to the input layer, we obtain an LP heat map in which the sum of the heat map pixels is equivalent to the final prediction score. So with the LP heat map, we can see what parts of the curve or features that has contributed to the decision of the network. So for a theoretical explanation of this LP method, please refer to the work cited here. So the leftmost figure here in figure 6 is our original plot of a mouse movement sequence, and the center plot here is the LP heat map computed, and the rightmost figure is a gradient heat map computed. So what are the differences between the LP heat map and the gradient heat map, and why do we choose to use the LP heat map instead of the gradient heat map to provide insights on the features learned? So from figure 6, it's apparent that the gradient heat map appears to be noisier than the LP heat map because the gradient heat map tells us what pixels in the image to change to have a maximum change in the prediction score. But that isn't our goal. What we want to know is what parts of the images actually contributed to the current prediction score. And for that, we employ the LP method. So here are more examples of the LP heat map. And if you look at figure 7 closely, you notice that there are two different colors here. So the blue region are simply negative evidences that are against the prediction, and the yellow region are simply positive evidences that supports the prediction. And what we want to know from these LP heat maps is what are the exact features that are learned by the network. Are they learning the start and the end point of the curve, or are they learning long straight line or kinks, or are they learning crossings as shown in figure 8? So from the LP heat map in figure 8, it seems that the network actually learns to ignore long straight lines and crossings. And if you think of it, it's logical for the network to actually ignore long straight lines because it's probably non-discriminative, it's non-informative, and this kind of information is probably not useful to for the network to use it to discriminate between users. And for the ignorance of crossings, if we were to use a time series-based model such as the LCM, these crossings wouldn't appear in the input data. But however, here it appears because we are just simply plotting the curve as a form of plotting the curve on an image to be used as an input to the 2D CNN model. So these crossings are simply just artifact, and this crossing shouldn't be used as a feature to discriminate between users. So we see that the network actually has the capability to learn to ignore artifacts introduced in the image. And in figure 10, we see that the LP heat map they are computed, they are not a complement of each other. That is, the negative region doesn't, the blue region here doesn't turn into the yellow region and vice versa. This makes sense because we know that the obviously classifier user 9 from Balabit data and user 7, they are not a complement of each other, so we can't expect the LP heat map that is computed to be a complement of each other. So this simply serves as a sanity check to check the correctness of our model. So as a conclusion, the 2D CNN model with multi-label joint training performs reasonably well, even though we have removed the temporal information, and the LP method helps us to obtain insights on the learned features in 2D CNN and showing a sparse distribution of relevant scores, and it learns to ignore artifacts introduced in the plots. Before I end the presentation today, there are some interesting questions which we would like to address in our future work. And one of these are raised by the reviewer. So one reviewer asked whether are these publicly available mouse datasets reflecting mouse behavior for user task pairs, or are they actually exhibiting long-term user trait? So to answer this question, we may require a new dataset with multiple tasks over time. And seeing how the performance of the model was severely impacted when the resolution during test time is different from the train time, we want to know whether a change in the exact physical screen size will affect the user's behavior, and how will it impact the overall performance of the model. And finally, can trust models from these two related works be used to reduce the overall impact of prediction errors? So that's the end of my presentation today. Thank you for listening. I'm happy to take questions.
Questions, discussions? Okay, so I will have a simple question. So usually when we talk about behavior authentication, we treat it as a verification problem, and we train a model for each individual user. So I think in your study, you treat this as a classification problem. So you train a model, a multi-class classification model.
No, I did not train a multi-class classification problem. Perhaps I can.
Right, you just have one model for end users.
Let me go
right?
to the figure. So, yeah, so here I have trained only one model for end users, but it
Right.
gives me an n different labels.
Right.
So one branch of the softmax layer here corresponds to one binary classification problem.
Yes.
So it's a binary classifier, but not a multi-class classifier.
Okay. So what if So in practice, these systems are dynamic, right? We always have new users and the existing users leave. In that scenario, do you need to retrain your entire model?
So if you have new users and you want to authenticate these new users, yes, you have to retrain the entire classifier.
Okay. But if you train a classifier for each individual user, you only need to retrain a classifier for that new user.
But if you think of it, the time complexity to train that a binary classifier would be the same as this, because for this we also need to retrain it only once.
Okay, yeah, that's okay. So any other questions? So let's thank the speaker again.